A lot of scientific research appears a bit too good to be true. Like it's a bit of a magic show. There is a set of tricks that aren't really meant to deceive us, and nevertheless, they're a bit incredible. The way that the analysis always seems to work out, even when the data collected aren't in any deep way logically connected to the scientific question. There's a lot of disbelief required from the audience, as well as from the investigators themselves. We're all willing participants in this. We don't mean any ill will or any deception. Few of us commit fraud, I hope. And yet, it's extremely difficult to find a logical track from the way data are processed to exactly what we're supposed to be learning from them about the world. Every experiment is significant, just like every Kleenex pops up out of the box. Every test gives us what we want. How do we do better? Let's pick up with where we left off in the previous lecture. This was the DAG, the directed acyclic graph, that I stopped with last time to remind you of the meanings of these variables. The G on the left is the cause of interest in this scenario. It's the grandparents' education within families. P is the parents' education, that is the children of the grandparents. And then C is the child's education, or the grandchildren with respect to the grandparents. In other words, we're interested in the intergenerational transmission of educational attainment within families. There's also an unobserved confound on the right, which represents some set of common exposures that parents and children share. This could be neighborhoods, cultural background, and so on. What's important for this example is just that those exposures are not shared with the grandparents. So, how do we use our knowledge of forks, pipes, and colliders to understand the implications of this causal model? Well, our goal is to estimate the direct causal effect of grandparents, not the total causal effect of grandparents. So if the graph was just this much, just a pipe from G to P to C with the direct path from G to C as well, then all we need to do is stratify by the mediator, by parents, to isolate the direct causal effect of grandparents on their grandkids. Unfortunately, since there's this unobserved confound on the far right, the shared confound by parents and their children, P is not only a mediator in this model, but it is also simultaneously a collider on the path I've highlighted here. And so that means when we stratify by it, to close the indirect path from grandparents to their grandkids, we end up opening this other opening a non-causal path through the confound to kids and biasing the inference. So in this context, we're left with only bad choices. We can either, on the left, estimate the total effect of grandparents on their grandkids with the model there that only stratifies by the grandparents' education. This is the total causal effect, and we can estimate it, but that's not our research goal. Our research goal was to isolate the direct effect of grandparents. Or on the right, we can attempt to estimate the direct effect, but end up with a biased estimate of that effect. Now, of course, if the unobserved confound is not very important, then the biased estimate on the right might be all right. That's a cost-benefit decision. But still, we're left with bad choices here. We can't really get the estimand of interest. Sometimes that's just how it is. What's important is to have a reasoned way to justify and clarify and communicate that trade-off transparently. For this example, which begins on page 180 in the book, there's a full drawing the owl, as it were, workflow. And I show you the important bits of it here, where there's a synthetic data simulation, and then we estimate the approximate posterior distribution for this example, and you can play around with the biasing effect and make it stronger or weaker, and think about that trade-off yourself. Why does this biasing happen, though? I think it's worth sticking with this example just a little bit longer because we're still trying to understand colliders. This is an example of collider bias. Conditioning on parents' education opens a non-causal path because P is a collider on the path that includes grandparents and the unobserved confound. What happens here is that stratifying by a variable means looking at the association between other variables only within each level of the variable you're stratifying by. I'll say that again. When you stratify by a variable, that means for each level of that variable, the stratifying variable, in this case, parents' education, you look at the association among other variables within each level rather than in the total sample. So in this case, this is what I'm animating on the right of this slide. We've taken the synthetic data simulation from the previous slide, and I'm showing you through animation the stratification of parents' education by pulling out clusters of points. So this graph has on the horizontal grandparents' education, and on the vertical child's education. That's the association we're interested in. And then we move from the bottom to the top through the centiles of parents' education, and this isolates different families. Each point is a family. And what I want you to see is even though, and I should say the red points are good neighborhoods. This is the confound in this example. And the black points are bad neighborhoods. And in bad neighborhoods, both children and parents have lower educational attainment. And in good neighborhoods, both children and parents have higher educational attainment. But that neighborhood is not shared by the grandparents because they lived somewhere else. So now as we move through the centiles, bottom to the top of the graph, we move through percents of parental educational attainment. And what I want you to see is even though the black points tilt up and to the right, there's a positive association between grandparents' education and child's education within each kind of neighborhood. Once we stratify by the parents, there tends to be a negative correlation. That is, the black regression lines I fit, most of them tilt down. And so when we average over the total sample, there's a negative relationship. But it's spurious. It's non-causal, this negative association. It comes from conditioning on a collider. An intuitive way to understand this is that there are two ways for parents to attain their education, either from their grandparents or from the neighborhood, from the unobserved confound. And when something like that occurs, that's the setup for collider bias. Okay, let's come back to our mission here. And how do we do better? That's how I opened this lecture. We do better by doing something akin to what we just did, which is having an explicit causal model. Maybe it's only tentative, but then we apply logic to explaining it and deducing the implications of it so that we can design an analysis strategy and communicate the estimates we get from it. In other words, it's a three-step project here with lots of details to be filled in depending upon the particular researchers and the particular context, but nevertheless, all of us need these steps. First is to clearly state our assumptions. It doesn't have to be a DAG. Could be something completely different, but it should be unambiguous. And second, we should deduce the implications from those assumptions. And those are implications both for what the assumptions imply about nature, about the phenomena we're trying to observe, and also implications for what's identifiable and estimable statistically. And then, of course, third, we test those implications. We carry out the implications of the deductions we've made. And that's drawing the owl, trying to do better than a set of illusions. So I'm going to spend this lecture talking about that in a more detailed way. We're going to take the basic tools from the previous lecture and stick them together into larger models and understand some of the standard threats and opportunities for inference that exist as a result of taking unambiguous models and making logical deductions from them about the implications of the theory and how we can process data statistically to get at the real estimand of theoretical interest. Before we do that, though, I want to emphasize something that I think is extremely important in this business of doing research, whether it's in academia or outside of it, is that We should strive not to be clever. And what do I mean? Well, I don't mean make yourself dumb by any means. I mean, don't rely on being smart enough to take every research question in context, in isolation, and just figure out the right way to get at the answer. This is not a reasonable way to proceed. It's not reliable. It can often fail. And perhaps more importantly, it's just not transparent. No one else should really believe that your clever response is necessarily true. Right? Just because you get the right answer, it could just be luck. And that means the method is bad and it'll mislead others in the future. So what should we do instead? Well, you know what I'm going to say. We should write unambiguous causal models. Again, they don't have to be DAGs. There are other ways to write causal models. They could be agent-based models. They could be differential equations. And then we use logic to derive the implications of those models. And those implications will give us predictions about the kinds of data we should look for to distinguish models, their truth value. And it'll also give us implications that we can use to design statistical procedures. And all of that can be done transparently because it is logical and algorithmic. In fact, you can make your computer do it. And later in this course, I'll show you how. Other people as well can use the same logic to verify or challenge your work. And this ability to audit the logical procedure is very important. In contrast, it's extremely difficult to audit cleverness. Okay, let's get to work. So in the previous lecture, I introduced the 4 elemental confounds. For 3 of them, when you study the first 3, the fork, the pipe, and the collider, you acquire the basic logical tools you need to analyze a DAG of any size, a directed acyclic graph of any size. And for causal models that aren't DAGs, that have more details built into them, these same principles hold. And so when you study the basic logic of the fork, the pipe, and the collider, and build bigger models, you can find that same logic in there. The same sorts of issues arise. So this is what we're going to do now, is think about how the basic implications of the fork, where X and Y share a common cause, and we separate them statistically by stratifying by their common cause, or the pipe, where X and Y are associated because there's a chain of causation from X to Z to Y. And again, if we stratify by Z, we statistically separate X and Y. And then finally the collider, which behaves in the reverse. X and Y both influence Z, and when we stratify, but they're not associated with one another because they share no causes. But when we stratify by Z, we end up inducing a statistical association between X and Y, and that association is usually going to mislead us unless we're careful. So for a DAG of any size, it's always composed of these same 3 fundamental types. Of course, there are also descendants, which I explained in the previous lecture, but descendants, in a sense, are also always part of either a fork or a pipe or a collider. So in this graph, for example, you can look at it and find a bunch of forks or a bunch of pipes or a bunch of colliders. And sometimes the same variable is in multiple of these. It might be in a fork and a collider at the same time, or pipe and a collider at the same time, as it was in the grandparent-parent-child example that I started the lecture with. But nevertheless, you don't need any new rules to understand the bigger structure. There are longer paths, but we understand them still with the same basic conditioning issues. What's the effect of stratifying by Z? We're going to get into that, and I'm going to show you some examples of how that works so I can build up your intuition and you can develop that skill. But first, I want to remind you, and this is very important to me, that theoretical models are in no sense constrained to be like DAGs. DAGs are a really great way to introduce this topic because they have very weak assumptions. They just indicate directions of causation between variables. But when you have a lot more scientific information, like, for example, in evolutionary biology and in population genetics, you can do much more powerful things, even sometimes with much less data. So the details of the plot on the screen here aren't so important. It's just to say that it's a wonderful thing about inheritance in simple animals like people with simple genetic systems, that those constraints are scientific information that we can build in statistical models to make fantastic inferences about, well, the history of our species and our population densities at different times, and even different features of our family systems, to speak casually. But let's get back to DAGs. We're going to stick with DAGs because I want this to be a general course that isn't specific to any one kind of specialty or subfield. And DAG thinking is a kind of thing that you can often use even in your own specialty because it's a good way to get started before you fill in the details. So the thing about DAGs is that they also help us understand experiments. They're not just for the so-called really difficult inferential research, that is observational studies. They also help us understand why experiments work in the first place, which is a very important thing because, of course, experiments don't always work. And when they don't work, we'd also like to be able to draw that into the DAG. So the thing to understand is that in an experiment, we effectively cut all the arrows that are entering the treatment. That is, all the causes of the treatment are removed because we, the experimenter, are the only cause of the treatment. That's what randomization is supposed to work, when it's effective. We randomize and we take a graph like the one in the upper right here, which is a relationship between x and y with some confound u. And when we randomize x, the treatment, we delete all the arrows entering x because we removed all the causes to x. We set x at whatever we like for every case or every participant in the experiment. But when there isn't randomization, what are we supposed to do? Those common confounds will make it impossible to get an unbiased estimate between x and y. Is there a statistical procedure in any particular DAG, any particular causal model, that mimics randomization? And the good answer is sometimes. Let's talk a little bit about notation, and then we'll get to how to figure out which times that is true. So we're going to introduce you to this do operator that I introduced actually in an earlier lecture very quickly. This py conditional on do x. I want you to read that capital P as the distribution of y. That's the probability, but we're talking about probability distribution. So just read the distribution of y conditional on do x is equal to the distribution of y conditional on what? So what does this do x mean? Do x means to intervene on x, to set it to some particular value. And what we're looking for, since we can't do the actual intervention in the graph, we're not doing an experiment, we're looking for some statistical manipulation, some set of variables to condition on so that we get the same result, so that the distribution of y conditional on doing x is equal to the distribution of y conditional on some set of information that we have. And it turns out, luckily, there is a way to analyze any DAG to figure out if such a thing is possible in general. And that's a wonderful achievement. So let me show you that. Here's a really simple example. This simple confound that I had on the previous slides. There's variables x and y. X is the treatment of interest, and y is the outcome of interest, but there's this confound. It's this path. The fork from u that connects to x and y is a non-causal path, and it ends up biasing our inference of x and y because the x and y are associated also through the non-causal path, through their common cause u. Now you know, because u is a fork, that if you condition on u, you can close the fork, and that means that any statistical association between x and y that comes from their common cause u will be canceled in our analysis if we can condition on u. So if we measure u, then it's a confounder, and we can stratify by it, and we can get a valid estimate of the causal influence of x on y. Okay, obvious enough. And of course, in an experiment, the equivalent information would simply come from ignoring u completely and randomizing x. And that's the relationship between the observational approach, where we find some set of variables to stratify by, to give us the same effect as deleting all the arrows that entered the treatment. Let me try to summarize a bit, and we'll march forward. The distribution of y conditional on doing x turns out to be equal to it's a weighted average here, is what I'm showing you at the bottom. It's not important necessarily to memorize this formula, but I want you to understand it a bit intuitively, at least for a few minutes. So what we're going to do is we find some set of variables to stratify by, and in this case that's x and u. Remember, we're conditioning on x because that's the cause of interest. We want to measure its association with y, and we also need to stratify by u because that's how we close the fork. So but u has multiple values in the data set. It's not constant. So for each of the values of u, we compute the distribution of y conditional on the value of x we've set x to. Remember, we're doing x, we're intervening on x, and then the particular value of u that's associated. And then the proportion, the probability of u means the proportion of the sample that has that u value. And all this sum does is compute the expectation, that is the average over the values of u of this association between y and x, having closed the fork. So the quote at the bottom of this slide is the thing that you can stick in your brainstem to help you remember. The distribution of y stratified by x and u averaged over the distribution of u. That's the intervention effect, right? So you can imagine simulating. To calculate the causal effect of intervening in this graph, you need to know the distribution of the other variables because they may also affect the distribution of y, as u does. But you get the right effect this way, and that's a magical trick. But of course, it's not a magic trick. It comes solely from logic, and we can justify it, and we can derive it, and we can prove it works through simulation and through mathematics. So the thing I want to emphasize before we move on and get to some exciting examples is that causal effects are not in general just coefficients in a model. They have been so far because the models we've used are extremely simple and the effects are purely additive. But in general, a causal effect, remember, a causal effect is an intervention. And the consequences of an intervention may depend upon all the variables in the system. They don't stop having causes just because we've somehow conditioned them out of our calculation and gotten the right coefficient on a particular variable. So what we need to know is the causal effect is the distribution of y when we change x averaged over the distributions of the control variables. In this case, it's just u. Let me give you a conceptual example so this makes sense. I appreciate that this is weird. This is a thing called a marginal effect. And marginal effects are the valid way to think about causal effects. So think about this cartoon case where we've got three variables. There are baboons and gazelles, and baboons do sometimes eat gazelles. Yes, baboons are large animals with very sharp teeth, and they like meat. And gazelles are made of meat. So also in these systems, I'm thinking of West African systems here, there are cheetahs. And cheetahs eat both baboons and gazelles. Cheetahs are at the top here. They're much more capable as predators than either of the other species. So if we go out to estimate the predation pressure of baboons on gazelles in any particular, say, game reserve in West Africa, the presence or absence of cheetahs is a bit of a confound because it influences the densities of both of the others. And in this cartoon example I'm making up, I want you to think of it this way, is that when cheetahs are present, in fact, baboons have almost no effect on gazelles because the baboons are scared. They're afraid to leave their trees, at least go very far from their trees, because they don't want to get chased down by a cheetah. But when cheetahs are absent, baboons rise to the top and they become predators. They become more fearless because the cats aren't around, and then they exert a lot more pressure on the gazelles. And so the causal effect of baboons on gazelles, on their densities, depends upon the distribution of cheetahs in a very strong way, in a strongly interactive way, non-additive way. And so if you're thinking about an intervention, you're going to add or remove baboons to some particular game reserve, the effect it will have on gazelles depends upon cheetahs. And so you must calculate the marginal effect. That is, you average over the distribution of cheetahs to understand what will happen, what the causal effect will be. We have examples of this in the course, and in fact, there's already an example in Chapter 6 where we simulate causal effects. Okay, the set of tools that are used to analyze a DAG and figure out which things you need to stratify by, which variables you stratify by to get a causal effect, is known as do calculus, from the do operator. Do calculus doesn't actually involve calculus. It's just probability theory and manipulation of graphs. But here calculus just means a calculation. So for DAGs, there's a set of only 3 rules. The do calculus only has 3 rules that will tell you if it's possible to find a statistical procedure that will give you the same information that an experiment would have, at least in theory. And that's the best we can do in this case, is in theory. Do calculus will say if it's possible, and it'll tell you what it is. And what's cool about do calculus in this case is it tells you what's possible to say before you pick specific functions by which the variables interact in the DAG. That is, remember, DAGs are in a sense anonymous about exactly how the x's and y's interact. They just indicate directions of causation. If you make additional assumptions beyond the DAG, that is, you specify the exact functions that we use, for example, in the synthetic data simulations we've done already in this course, then often there are additional implications, and you can exploit those and have more power quite often through those additional assumptions. DAGs are in that sense both a worst case and a best case scenario. So they're a worst case scenario in the sense that additional assumptions will often give you stronger inference. The DAG is a very weak case because you've assumed very little, you've left it quite vague, you've just drawn some arrows between variables. And do calculus just tells you what's decidable in that very vague case. Do calculus is also a best case scenario at the same time because if some causal inference is possible just from the do calculus, then it doesn't depend upon special assumptions. And that's a very general and defensible position that a lot of us would like to be in science because often we don't know exactly how variables interact functionally. And so if the do calculus tells us we don't need to know that, then that's great news. On the right on this slide, I have my favorite picture of Yuta Pearl, who's the father of do calculus. Pearl is a quite famous computer scientist and statistician, and do calculus was built on the work of many, many other people, but Pearl made an incredible contribution to this literature. Okay, one of the most useful implications of do calculus is this thing called the backdoor criterion. And the backdoor criterion is in a sense a shortcut to applying do calculus in a particular way. Do calculus is bigger than the backdoor criterion. I'll say a little bit more about that later. But the backdoor criterion is the first really useful tool you're going to get from it. And you'll apply it all the time in thinking about causal models. The backdoor criterion is a way to analyze graphs to find sets of variables we need to stratify by, but it also helps us design strategies for research at the same time, because if we sketch hypothetical graphs, we can think about using the backdoor criterion when something is identifiable or not through the variables we collect. Okay, what is the backdoor criterion? It's a rule for finding a set of variables to stratify or condition by to yield the distribution of y conditional on doing x, as I've explained before. And there's really only 3 steps to this rule. The first is you identify all the paths in the DAG that connect the treatment x to the outcome y. So if you look at the example DAG on the right of this slide, with 4 variables, a path means a set of connected nodes, either going with or against arrows, but that runs continuously without loops from the treatment x to the outcome y. I'll step through this DAG in a couple slides and show you those paths. Second, once you've got all the paths connecting treatment to the outcome, you focus your attention on the paths that enter x, that is, their arrows hit the back door of x, and these are called backdoor paths. Backdoor paths are non-causal paths because causes exit the front door of x, as it were. Third, I should say, but backdoor paths can certainly create associations, as in the case of confounds. Third, we find what's called the adjustment set that closes or blocks all the backdoor paths. And the adjustment set are the set of variables we stratify by that will close or block all the backdoor paths. So let's walk through an example here. Here's step one of applying the backdoor criterion. We identify all paths connecting the treatment X to the outcome Y, and there are exactly two in this simple DAG. There's a direct front door path from X to Y, shown on the left, and then there's the backdoor path that goes from X to Z to U to Y. And that second path is a non-causal path, the backdoor path. So that's, according to step two, that's the one we focus on because it's non-causal. And we need some way to block that path so it doesn't create phantom associations that we may interpret as causal. So in this case, good news is you can just stratify by Z. There's a pipe from U to Z to X that the association is transmitted along. And so X ends up being independent of U if we stratify by Z, and that closes the backdoor path, just by the rules of you learned in the previous lecture about how to close a pipe. And then the causal effect, the distribution of Y conditional on doing X, is again given by fitting the model that has both X and Z in it. That is, you stratify by Z while considering the association between X and Y. And then you average over the distribution of Z in your sample or in some hypothetical sample to get the estimated causal effect of intervening in some particular population. Okay, that one was easy, I hope. Let's take something a little bit more advanced, a DAG with a few more elemental confounds in it, glued together like Lego blocks. In this case, what we want to do is analyze this graph using the backdoor criterion, list all the paths connecting X and Y, and then consider which need to be closed in order to estimate the effect of X on Y. So there are three paths in this case that connect X to Y. There's the direct path on the left. That's a front door path. It's causal. There's the path shown in the middle, the pipe going from X to Z to Y. That is also a front door path, is also causal. And then finally on the right, the pipe going from, the collider path from X to C to Y. C is a collider in this case. This path is also a front door path, but it's not a causal path. It doesn't create any causal association between X and Y because it's a collider path, and the cause from X goes to C, but there it stops, at least in nature. And unless statistically, if we condition on the collider C, of course, bad things could happen. So in this case, what's the adjustment set? What do we need to condition on in order to estimate the causal effect of X on Y? And the answer is nothing. We should not condition on Z because that would block one of the causal paths. Z is a mediator of the total causal effect of X on Y, so we shouldn't stratify by Z because that would lead to us blocking the indirect path, but that's part of X's cause on Y. And we definitely shouldn't condition on C, the collider, because that would create a bias in the sample. That would open the collider path and create a phantom non-causal path. Let's let's level up a bit to another example. We've added some more elemental confounds to this particular DAG, and let's go through the same exercise. We're going to break this down into its individual paths. And I want to show you how algorithmic this is, and then we consider each path in isolation, and we build up the adjustment set iteratively. You can take your time and do it right. Before we do that, I want to show you the animated version of this so you can get an idea in a DAG like this, which is really not that complicated compared to natural systems, how many indirect effects there can be passing between variables. So I'm going to start the animation here, and each causal variable is going to have its own color. And so sometimes the circles will be filled and sometimes they'll be open. That's just meant to represent that the values are fluctuating. But the values are always the same as on all the arrows that travel out of the variable. So we begin, A and B and C have their causes, then they hit the other variables, And you get these little flower petals that rotate around the causes, the direct causes, and those represent the secondary effects that have been passed on. That is, for our cause of interest here, X, there are 3 other variables that have, in a sense, contaminated it, because there are 3 arrows entering it. There are 3 backdoors, as it were, and those make it so that the direct causal effect of X can be difficult to detect without doing something clever statistically. So what can we do here in order to deal with the fact that X has all these indirect effects that make it difficult to tell what it's really doing to Y in isolation? Well, we're just going to break it down as we have done before. One way to think about this, of course, is that what we're trying to find is a statistical procedure so that the situation on the left, where we've got these backdoor paths, the highlighted red arrows that are causing us grief, we want a statistical transformation to the data so that we can have what's on the right. We're trying to statistically mutilate the graph, as it were, and delete the backdoor arrows as if it were an experiment. And we do this by breaking down all the paths and considering them one at a time. So let's do that. There are 6 paths that connect X to Y in this example. Let's take them one at a time. So in the upper left, that is the direct front door path from X to Y. That's actually the target of our inference. That's the estimand. So we definitely don't want to block that path. So let's keep that in play. The second path here in the top middle, this is a collider path. This is like the previous DAG example. This is a confound now. So this is a fork. C is a fork, a common cause of X and Y. And that's a confounder. And so we're going to need to condition on C. We're going to need to stratify by C to block this non-causal path. Similarly for Z, we have another fork, another confounding path. Z is a confounder, common cause of X and Y. We need to stratify by Z as well in order to get the do inference, to do X. Then in the lower left, there's this long path over the top. It's a backdoor path because there's an arrow entering X at the start of this path. It goes to A and then to Z and then to B and then to Y. This path has a collider in the middle. Z is a collider. You see, because A and B influence it and it's in the middle of the path. So this path is closed, but we just learned that we had to condition, we had to stratify by Z. And when we do that, that opens this path. So this path will be open, which means we need to find some other way to close it. And we've got options. We've got A and B. If we stratify by either A or B, in this case, we can block that overhead route, as it were, the path from X to A to Z to B to Y. The other paths are special cases of just composites of the other paths, and so we don't need to consider them by themselves. They'll be blocked just by conditioning on the ones we have listed here. Our adjustment set is C. That's a confound. We need to stratify by Z, which is the other confound we must stratify by, and then either A or B. B turns out to be the better choice for reasons I'll explain later in the lecture. But just take my word for it now. But A would work too. It's just less efficient. It's not as good as choosing B. But what's important to understand is we need to choose either A or B because conditioning on Z opened that collider path at the top. And that happens sometimes. These things, because a variable can be in multiple paths at the same time, we have to be careful about what happens when we condition on any particular variable. It may open other paths or close paths that we want to stay open. If this seems complicated, that's perfectly normal. The first time I met this stuff, I thought it seemed insane. But you get good at it quite rapidly, actually. And after a little while working with DAGs, you can analyze them with your eyes. Just trace the paths with your eyes and see what's going on. It's like learning a foreign language. At first, it's just noise. But after a little bit of experience, you know where the words begin and end. And then after a little bit longer, you start to understand parts of it, and you can say things and order dinner and so on. DAGs are much simpler than learning a foreign language, and you'll get better at it quite fast. You just need to be patient with yourself. It helps a lot, though, in learning to use some automated tools. The backdoor criterion and all the other rules of due calculus are, in fact, algorithmic. So robots can do them, and they do them better than we do. There's this fantastic website called daggity.net. I put the URL at the top of this slide. And if you go there, you can draw in your browser and with your mouse DAGs and connect the arrows, and then Daggity will tell you the adjustment sets that are required for any particular treatment or exposure. I think that Daggity calls it any particular exposure and any particular outcome variable. So here I've drawn the DAG example we just finished, and you'll see in the upper right it's showing you the minimal adjustment sets, C and Z, and then either A or B. It'll also show you other stuff, the so-called testable implications in the lower right. These are all the conditional independencies that are implied by the DAG, and I haven't emphasized these, but I talk about them in the book. This is a way to actually test the structure of the DAG itself with your data. Okay, back to the backdoor criterion. So, as you know, this is a rule for finding adjustment sets. And the examples I just showed you were meant to emphasize that you have to be careful that when you stratify by one particular variable, you don't end up opening or closing other paths that you didn't want to open or close. Due calculus is more than backdoors. It can also provide solutions, that is, statistical procedures that involve simultaneous equations, and so don't really resemble simple regressions of the sort we've done so far. Instrumental variable techniques are an example of this. And of course, I showed you an example a couple lectures ago of something I called jokingly full luxury Bayes. You can simply program the entire causal model as a Bayesian graph model, a set of simultaneous equations, put them all in QAP, or later on we'll put them all in the same Markov chain, and run all the submodels together. And this isn't indeed a simultaneous equation approach, and that can work as well. In a sense, it kind of substitutes for due calculus because if an inference isn't possible, then the posterior distribution won't produce one. You'll get the prior. Nevertheless, due calculus remains extremely useful for Bayesians. I hope I've convinced you, because it gives us a set of intuitions about the kinds of designs and analyses that are possible and efficient. And we need that kind of insight, even if full luxury Bayes is going to do the calculations without needing due calculus to provide an estimator of any kind. Because, of course, in Bayes, the posterior distribution is the estimator of interest. The other great thing due calculus does for us Bayesians is it tells us we don't need all the variables. Sometimes we can save ourselves a lot of grief because due calculus will say that a lot of the variables, a large section of the DAG, is ignorable. And that's good news because it makes our life easier. Okay, I think we've earned a break, and at this point you might want to flip back through the slides and think about the bits that were confusing, or maybe I went over a few things too quickly, and make some notes, and then take a break, get a snack, walk around, and when you come back, I will be here waiting. Okay, welcome back. I hope you had a good break. Before we get back into the material, I just want to make a little pedagogical note here. There's a lot of material in this course, and a lot of it's quite technical. And the thing that always strikes me about material like this is that the students really do all the work. I lay out some things for you, organize the material a bit, but just like the birds in this cartoon who learned to fly, really the potential is in the birds all along, and it's their own work and practice and the falling down they've done and eventual flight that makes them successful. And the same is going to be true for all of you learning this material. Really all I've done is provide a bit of a softer playground for you to learn this material, a gentler ramp, as it were, to get into the material. But you still have to do the work, and so at any point you're finding it a bit confusing or difficult, I just want you to know that that's normal. Just like birds don't immediately learn to fly, no scientist immediately learns how to do statistics. Okay, back to the material. There are lots of things we can do with the do calculus, as it were. And I want to leverage your new powers of thinking about the backdoor criterion and how to trace paths in graphical causal models to talk about a very important applied research issue that is something that's very practical for doing research, and that is the topic of good and bad controls. A control variable here means a variable that we introduce to an analysis just for the sake of getting a causal estimate for some other variable. Control variables are extremely common in all scientific fields because all scientific fields recognize the existence of confounds. And there are a bunch of heuristics for deciding which control variables people will use. The most common of these is just anything you've measured, anything in the spreadsheet. Control all the things. This is a very bad idea, and I want to show you some examples of why that's the case. Another heuristic would be any variables that are not highly collinear. This is also not a good idea. Collinear means that they have a high bivariate correlation before they're put in the model. The trouble is that high correlation could arise through lots of different causal relationships between the variables, and sometimes those relationships are harmless, and other times they interfere with our inference. Another common heuristic for choosing control variables is that anything that is measured before the treatment is applied, a so-called pre-treatment variable or a baseline variable, is fair game to add as a control variable. This is also not always true, and I'll show you an example. Okay, for the examples to come, all of these come from this fantastic paper that I give you the citation to at the bottom, a crash course in good and bad controls. In each of the examples, we're going to be interested in the causal effect of a treatment X or some cause X, some exposure on an outcome Y. The first example I want us to consider has two unobserved variables that nevertheless have causal influence, the very important causal influence. So now there's a variable u, which is unobserved. The dashed circle in these examples will mean that we have not measured it. And u is a fork. It is a common cause of x and this other variable z. And then there's another unobserved variable v in this example that is also a fork, and it is a common cause of the outcome y and the same z that u influences. So z is a collider. It's a collider of u and v. Now in this example, what should we do? Should we control for the variable z? I want you to start thinking about that as I explain the example in terms of some more real-world variables. So this kind of situation shows up a lot in social network problems. So imagine, for example, that X is the health of one person in a community. Let's just call them person one for the moment, first person in a dyad. And Y is the health of person two. What we have in mind here is that there's been some change in person one's health. Maybe they gained some weight, or they had a heart condition develop. They started smoking, something like that. And then later on, person two also, or not, experienced the same change in status. But it happened to person one first. And we're interested in whether or not the change in person one's health status directly influenced the change in person two's health status through some sort of social transmission, as it were. Now, in this case, the unobserved variables could be lots of lifestyle things, like hobbies. Let's just say it's hobbies, the kinds of recreational activities that person one and person two like to do. And so U is the hobbies of person one, and V is the hobbies of person two. These two things influence the health of person one and person two, as hobbies do. Right? If your hobbies involve jogging, that'll have a very different health effect than if your hobbies involve watching Netflix. But these hobbies also influence becoming friends. And so now Z is the status of being friends or having a particular kind of tie in a social network. And so if we add friendship status to our analysis, thinking it's a good control, right? Because that might influence the strength of the relationship. We actually create a confound in this example because now we've opened a non-causal path, a backdoor path, from X through Z to Y, and we've biased the inference. So let me show you that graphically and what's going on here. So let's apply the backdoor criterion. We're going to list the paths. The first path is just the direct path from X to Y. That's what we'd like to estimate. And there's one other path, and it's this long path that winds over the top here, from X to U to Z to V to Y. And since Z is a collider, as long as we haven't stratified by Z, this path is closed and does not create a bias in our inference of the causal effect of X. This first path is a front door path, and it's open. And the second path is a backdoor path, so it's potentially bad, but it turns out luckily to be closed. However, if we add Z as a control, trying to be clever, it will actually create a problem for us. This is a bad control. There are no backdoors to close here, so we should not condition on Z. So this is just a summary of the example I just gave you. What happens when you stratify by Z? You end up opening a backdoor path that would have been closed by default otherwise. The important thing to note here is that Z is a pre-treatment variable. The friendship could have existed before the change in health status of person 1. It's a pre-treatment variable, but it's still not safe to condition on it because pre-treatment variables might share common causes with the exposure, which is X in this case, and or the outcome, Y in this case, and therefore there's a potential collider bias lurking in the graph. Let's think about another example, and yes, this also has a collider in it. Most of my favorite examples do. In this case, we've got a simple confound between the variables Z and Y, but we're interested in the causal effect of X on Y. So Z is a mediator of the causal effect of X on Y. If you want to think about this in terms of some real-world variables, maybe X is winning the lottery and Y is your lifespan. So we'd like to measure the effect of someone winning the lottery on lifespan. And Z is a mediator of this relationship. It's the happiness effect of winning the lottery, and happiness may also extend your lifespan. And happiness and lifespan are confounded by a bunch of contextual variables that aren't shared with winning the lottery because winning the lottery is exogenous and random, right? It's like a treatment in a sense. It's totally randomized with respect to everything else in this graph. So let's do the backdoor criterion and figure out if there are anything we need to control for here to estimate the direct effect of X, the causal effect of X on Y. So what are the paths? There are two. There's the the pipe from X to Z to Y. And then there's the path through the confound U, the unobserved variable U. That's X to Z to U to Y. There are no backdoor paths here. Since there are no backdoor paths and no open non-causal paths, Z is right? We haven't conditioned on Z. So the collider is not open there. There's no need to control for Z, and a simple regression of Y on X gives us what we need. But if you do condition on Z, then some terrible things can happen. Here's some code if you want to play around with this and get an idea how to explore and simulate these scenarios. Remember, there's no need to try and be clever. Instead, be algorithmic and methodical about these things and just apply the rules relentlessly. Be relentlessly logical because then your colleagues can trust you. Your colleagues, if you're clever, your colleagues can't trust you because they can't audit your cleverness. So let's be relentlessly logical here. What I'm doing on this slide is I'm writing a simple R function that will simulate from this causal model. I've had to assume some specific functional relationships, and I've just made them simple and additive for the sake of the example. And by putting this little simulation and then it runs two regressions, I should say. So the data are simulated. We get simulated values for x and u and z and y according to the arrows in the graph on the right. And then two simple regressions are run. And I just used the linear model LM command in R for expediency here. And then the first is just a regression of y on x, no controls. And then the second is adding z as a control. And then from each of these, we just pull out the coefficient on x, and then it's returned by the function. And then the line that begins with the symbol sim and uses MC replicate, that means multi-core replicate, runs 10,000 of those simulations and collects all the coefficients. And now I'm going to plot for you the distribution of those coefficients. And I want you to see the effect of conditioning on z. So the black density on the graph in the lower right is the correct density. You don't always get the data generating value back. The data generating value in the simulation is 1, right? You'll notice the density is centered on 1. But of course, there's variation across simulations. That's just how research is. But this is what you want to see when you're validating an analysis. And then the red density is from the regression where we've added z as a control variable. And this is a bad control here, adding it in here. Now, you already saw in a previous lecture that when you condition on a mediator like z, you can block the treatment effect. What happens here is much worse than that. And the reason is because the mediator shares a confound with the outcome. And so when you condition on the mediator z, you turn on that confound that previously was ignorable. You didn't need to measure u. But as soon as you condition on z, you've turned it on, and it invisibly biases your inference. And I want you to see it actually flips the sign of the coefficient, and it's now negative, centered on minus 0.5 instead of on 1. So this is much worse than what happened in the previous case where we conditioned on we stratified by a post-treatment variable. So I can emphasize this. We can run it again, and we can change the causal effect of z on y to 0, and this will really bring it home for you. I haven't changed anything in the code except one little part on the line that starts with sim. I've just set bzy, which is the path coefficient from z to y to 0, and I rerun it and redraw the densities in the lower right. Now the correct density, the black density, is centered on 0 because I've made the causal effect of x on y 0. Why? Because x influences z, but then that influence is not passed on to y because the path from z to y is 0. So there's no causal effect of x on y in this example. However, when you condition on z, you create a confound that tells you there is, and there's a reliably negative relationship between the two. But that's just the confound being activated. Z is a bad control. Okay, this is just a summary of that example. There are two paths here, no backdoor, no need to control for anything. When you do control for z, you create a bias and get a biased estimate of the treatment x. Post-treatment bias like this is unfortunately rather common. I've cited this paper in a previous lecture, but I'm going to do it again in case you missed it. This is a survey from political science, top journals in political science, many experimental studies, and around half of them are doing some form of conditioning or stratification by post-treatment variables. Note that this includes cases where you drop cases from the data based on post-treatment criteria like attention checks and such. Those things can also lead to the same kind of biased inference. If you want to understand that better, I highly recommend this paper. You should take a look. It's worth your time. Okay, you know all about colliders. I hope you like them as much as I do. You know if you see a graph like this that you don't touch the collider. Z is a collider, leave it alone. It's like the third rail. But colliders are not always so obvious. They can also be lurking due to the existence of unobserved variables. So here's a case where it's not a classical collider, but there's a fork from this unobserved variable u. U is a common cause of the outcome y, and when z is a consequence, a descendant, as we call it in these graphs, of x. And so If you want to understand the causal effect of x on y, it's easy here. Just don't condition on anything. But if you do condition on z, bad stuff happens. What would be an example of something like this? Well, off the top of my head, x could be educational attainment, y could be income. We could be interested in the causal influence of education on income. Lots of people in education and economics are. And z could be something like a person's values, which are often affected by education. The unobserved confound could be something like a person's family context or family background and the cultural influences of that background. And that could jointly influence your income because it influences the kind of job you take and how you conduct yourself in the workplace. And it could also simultaneously affect your values, a set of values that don't directly influence your income. If you condition on the values in this case, because you're thinking that some value does directly influence income and you want to control for it, you would actually activate a confound in this example. So beware. Here's a more elaborate example. It's usually called case control bias in literature. This is a really simple graph, and you might think, what could possibly be going on here? This is just a pipe, but it's a pipe where we're interested in the causal relationship between only the first and second variables, and the third one is the one at the end of the pipe is the one we're considering now. Should we add this to our analysis? And the answer is no. Please don't. What's going on here? Well, here's a possible example you could help you think with. Maybe X again is education, maybe Y is occupation, the type of job a person has, and Z is the income, which is a consequence of that occupation. If we want to understand the causal influence of education on occupation, we should definitely not control for income, at least not if the causal relationships look like this. And the reason is because when we do that, we end up removing variation in occupation that Z shares with occupation, and there's less for education to explain. Let me show you what happens in this in terms of code. You can see it in this case. So again, a simulation, same structure of code as before, but the details inside the function f are different. They correspond to the graph on the right, and I've made the path coefficients, that is the causal effects of each variable on its neighbor, equal to 1. Right, so the total causal effect of x on y is 1, and of y on z is 1. Now we run two regressions again, y on x and y on x with z added as a control variable. We run 10,000 simulations, and we plot the distribution of the posterior means from those simulations for x, the coefficient for x, the exposure. Again, the black curve is the correct one, and it's exactly where it should be, right over 1. And the wrong one is half that. It's right over 0.5. And this is the effect of when you condition on z, you've effectively statistically explained away half the variation in y, the variation that y shares with z, and then x doesn't have as much to explain anymore statistically. It's like you're splitting the explanation of y between x and z. But z is not a cause of y. But the statistical model does not know that. I'll say that again. Z is not a cause of y, but the statistical model has no way of knowing that. And so it proceeds as if it was just supposed to predict it, measures the covariance with it, and ruins your day. Let's think about the other end of a DAG where we put Z on the end. It's still a pipe. Now there's a cause Z that influences our exposure of interest X, and then X influences Y. This is a situation which I call a precision parasite. This is my terminology. If you've got better terminology, I'm happy to adopt it. This is a case where there are no backdoors. There's no backdoor because even though there's an arrow entering X from Z, that path stops. It stops at Z. It doesn't continue on and connect to Y. So it's not a backdoor path. But it's still not good to condition on Z in this case. And this is a bit counterintuitive, and this goes beyond the backdoor criterion, but I wanted to show it to you so you get a sense that there's more out there lurking in specific functions and causal systems than just backdoor paths. So again, on the left in the code, I write a function that simulates from the DAG on the right, do 10,000 simulations, collect the posterior means for the the simple regression of just y on x and the regression that includes z as a control. What I want you to see in the densities in the lower right is that there's no bias here. So the black density is the right one. It's over 1, and 1 is the correct causal effect of x on y. That's what I made it in the simulation. And then the so-called wrong one, the regression that includes z, it's also centered over 1, but it has higher variance. It's less accurate. And so this is what I mean by a precision parasite. When you include in a regression a cause of the exposure, it tends to remove variation in the exposure to explain the outcome of interest. And this reduces your statistical efficiency. And so it's usually a bad idea to do this, unless you use it in some particularly clever way. And a more elaborate case of the precision parasite that is definitely not just a small loss in efficiency is this phenomenon called bias amplification. This is a case where, again, x is going to influence y, and the two are confounded by an unobserved variable. That's bad news. And then there's a cause of the exposure z. Z is not confounded. Now, we can't get, with this graph, you can use your powers of do calculus, your finely tuned powers of do calculus to analyze this graph with your eyes and see that there is no way to get an unbiased causal inference from this graph unless we can measure u. Well, there may be a way. We'll talk about it much later in another lecture. But for now, with what I've taught you, there's no way to do it. Now the question is, what happens when we add z to the model? Does it do nothing? And the answer is something really awful happens. It makes everything worse. And so here's what's going on. Again, here's a simulation just to show you what happens. I've made all the causal effects 1 in this case, so it's easy to think about. The regression of y on x is biased. I made the true causal effect 0 in this simulation. So the black density, if we had an unbiased estimate, would be right over 0. The place on the x-axis where the little tiny arrow is pointing. But it's not. It's biased. It's much higher than that because of the unobserved confound u, which is shared by y and x. But the regression that adds z, the cause of x, is even more biased. Even more biased. So this is why this is called a bias amplifier. Causes of the exposure are typically bad news in typical regression models, and you almost never want to add them. Why? What is happening here? This seems almost as a perverse sort of event. Here's one way to think about this, and I got a couple slides to try and explain it to you. To measure the covariation between x and y, or for there to be any covariation between x and y, we require variation in their causes. That is, two things can't covary unless they vary in the first place. Yeah? And so if there's variation in the unobserved confound u, for example, then that can generate greater covariance between x and y. But if there's a very little tiny bit of variance in u, the unobserved confound, then the amount of confounding it induces must be small. The amount of covariation it induces between x and y must be small. Similarly, if x doesn't vary very much, it stays in a tight range of values, then its causal effect on y can't be very large. And then also for z, if z doesn't vary a lot, then its causal effect on x can't be very large. And then u will explain most of the variation in x. Now, statistically, you can remove variation by stratification. And so if we stratify the sample by z, which is what happens when we add z to the regression. Remember, it's adding a predictor to a regression model means, or effectively means, the association among the other variables is measured for each level of the control variable that you're stratifying by, in this case z, and then you average over the distribution of the control variable, in this case z. But the association is measured within each level. And so within each level of z, there's less variation in x, because you've removed all the causal effect of x on z when you look within each value of z. I'll say that again. I know this is a bit weird. Within each level of z, there's less variation in x. If z completely determined x, there would be no variation in x for each unique value of z. But of course, that's not true here. X has some other noise to it, and it's also influenced by u. But nevertheless, if you look at all the x's which share the same value of z, they're more similar to one another because they share the same cause z, the same value. And so within each level of z that you stratify by, there's less variation in x. And that means there's relatively more variation within each level to be explained by the confound u. And when you stratify, that's what the model is doing. The regression is looking within, and so it gives more weight to the confound. Isn't that terrible? It's just terrible. Here's a graphical version of that, maybe prime your intuition a little bit. So it's the same graph, and I've just done a one-off simulation here, but I've done it with continuous variables to help you see what's going on. And to make this maybe pop a bit for you, I've made the causal effect of x on y exactly 0. So there's no covariance between x and y is induced by x as a cause. It's all the confound. And so we simulate a total data set here. The red points are the case where z equals 0, and the blue points where z equals 1. And the black regression line is the total sample. As you can see, there's nothing much going on there. That's the 0 effect, the lack of association between x and y. It's biased a little bit by u. Yeah, it tilts up a little bit. Just a small confound. But then if we stratify, we look within the red points and within the blue points and draw regression lines within each of those, you'll see that they're much steeper. And that's because, as you can see, each of them covers a smaller range of values. The red points are much narrower than the total sample, and likewise the blue. So there's less variation to be explained by x, and we end up with this more of the covariation being explained by the confound. And so within each cloud of points, red or blue, the confound is creating the tilt of those points, even though in the total sample, the tilt is very small. These are the sorts of weird statistical things that happen when you add bad controls. There are also good controls, and we talked about those before the break. I apologize for all of these examples being a bit bad, as it were. But that's the yin and yang of this stuff about using statistical models. Just like you have to be careful not to omit important confounds from your model, you have to be careful not to add them as well. Heuristics really fail. You need some logical procedure, like the do calculus, or for a more elaborate causal model with all the functions embedded, you need to analyze it and figure out deductively which information needs to be included in the statistical version of the model. Okay, I think we should take another break. This is a very long lecture. I'm really feeling it. And so let's take another break, and maybe you want to wait till tomorrow to finish this, or even the day after. But at the minimum, I think you should flip through the previous slides at least, have a glass of water, go for a walk. But whenever you come back, I'll still be here. Okay, I'm going to finish up this lecture now rather rapidly by talking about a topic called the Table 2 fallacy. And this is a bit of advice that connects this business of using causal models to design statistical models, that connects that to publication strategy and how we communicate results to our colleagues. So, what does the Table 2 refer to here in Table 2 fallacy? Well, it refers to this convention in many fields that the first table in a paper is a set of descriptive statistics about the sample, how big it was, and just marginal distributions of each of the measured variables, like the age distribution and so on. And then Table 2 is a set of model coefficients, that is, its regression output or some other kinds of statistical output. And the thing about these tables, I just give you a random example that I pulled up off my computer on the right here, is that not all the coefficients from a model are causal effects. You know that already. But in these tables, there's no information to help you figure out which are causal effects and which are not. And the problem's deeper than that, because some are causal effects, Some are total causal effects, and others are partial causal effects, and others are just confounded hopelessly. And you can't tell just from the table which is which. So it's very dangerous to read these tables, perhaps even to present them, because it's far too easy for a reader to interpret everything in here as a total causal effect. In fact, you know this happens all the time, and we should never do it. The basic reason this is a problem, you've already learned. A statistical model that was designed to identify some particular estimand, like the causal influence of x on y, is not going to also magically identify the causal effects of all the control variables. The control variables are just there to block backdoor paths. And their coefficients may have no important meaning at all. And it may not even be necessary to purport them in the paper. I'm going to give you an example now of this. This example comes from this fantastic, short, and very easy to understand paper by Westreich and Greenland, published in 2013, called The Table 2 Fallacy. I highly recommend you take a look. It's just a handful of pages long, and it's really well written. So the example they use is an epidemiological example. So imagine you're trying to study the effect of HIV infection on risk of stroke. That's in the center of this graph, the influence of X on Y. And there are a couple of other variables that are known to influence both HIV and stroke. So one of these would be smoking status. Smokers have depressed immune systems and are more likely to acquire an infection. And they're also more likely to develop all manner of heart disease, including to experience stroke. Then age is a risk factor. Increasing age is a risk factor for all of these things as well. It's a risk factor for smoking. It's a risk factor for infection, and it's a risk factor for stroke. And so we get the DAG as pictured here. I'm going to spend a moment animating this for you, like some of the previous animations, and maybe that'll give you a little bit of appreciation of what happens as the causes cascade through a graph like this. You can see that there's a lot of indirect effects, especially from age. So all the blue that's piling up on the right by the outcome Y are effects of age, either direct or indirect. Right, so when blue is in a ring, those little flower petals around the other colors, that means it's an indirect effect. That is, some causal effect of A has been passed on through another path. And our goal is to somehow decontaminate X of the blue and green that's circling around it on the right. Those backdoor effects that it has inherited from smoking and age. Okay, and we can do this. You're a pro at this now, right? We just used the backdoor criterion. So let's list all the paths. The first is the direct causal path from X to Y. That's the object of our affection, and we're going to estimate that. The second is a backdoor path that has smoking status as a fork that connects the exposure to the outcome. The second backdoor path has age as a fork connecting X to Y. And then finally, there's this longer path. It's another backdoor path, passes through age, but then it goes through another variable, through smoking, and then onward to the outcome Y. But it's another backdoor path. We need to close these three backdoor paths, and I think you can probably see how to do that. We just need to stratify by both age and smoking status, and we can close all three. And then we can really estimate, assuming this graph is true, the effect of HIV infection on stroke. Okay, so as sticking with simple regression examples for this part of the course, the regression you need to run includes terms for X, for smoking, and for age, as seen here. And these terms might be more complicated if you think the functions that relate these variables to one another are not perfectly linear. But for the conceptual lesson here, that's not important. Now what I want to do is we're going to take each of the variables on the right-hand side of the linear model, that is on the right-hand side of mu, the X and S and A, and we're going to look at this regression from their perspective, as if they were the estimand. So let's start with x. X really is the thing we want an estimate for. We want our estimand is the causal effect of x on y. From x's perspective, the regression's all about it. And the unconditional covariance or association between x and y is confounded by a and s. That's what we just deduced from the backdoor criterion. When we condition on a and s, we stratify by a and s by including them in the model. It closes the backdoor pass. It's like they've been statistically deleted. And then the coefficient for x measures the effect of x on y. Just a note here, you still need to marginalize this causal effect. It's like the coefficient of x on y is what you need to compute the causal effect, but you still got to pick values for a and s for any particular target population, because a and s are also risk factors. And so if the model's got any nonlinearities in it or interactions, then the actual causal effect of x on y will depend upon the age distribution and the frequency of smoking in the population. And that's that marginal effect issue that I mentioned much earlier in the lecture. Now let's take the same model and the same DAG, and let's reconsider it from the perspective of S, that is from smoking status. Now the regression's all about it, right? Because structurally there's nothing to say that it's not the target of inference here. In the unconditional model, the effect of S, that is the association between it and Y, is confounded by A because there's a backdoor path, right, that contaminates, that arrow from A that enters S, that contaminates inference about S. But when we condition on A and X, that backdoor path gets closed. But now what is the coefficient on S in this case? Notice that S has a total causal effect through two paths. It has a direct effect, that is the arrow at the very top of this DAG, the one that remains on the right. And then there's the indirect effect through X that's mediated by X. And that one is removed by conditioning on X, right? Because when you condition the path from S to X to Y is a pipe, and when you condition on the variable in the middle of a pipe, you close the pipe. And so we've closed the pipe. And so the coefficient on S here is not the causal effect of smoking. It's the partial causal effect of smoking. It's just the direct effect, which could be small. It could be large. We don't know. But nevertheless, this coefficient means something different than the previous one. And now finally, there's a third variable. We're going to look at this again from the perspective of age. Age rules this DAG. It's totally in control. It has causal effects through every part of it. And the total causal effect of A on Y flows through all paths. So actually, if you wanted to measure the total causal effect of age on stroke, you would just regress stroke on age in this model, and you wouldn't condition on anything. Because all of those paths are front door paths, nothing is confounded, and you need to account for all of those paths to measure the causal effect of age on stroke. What happens when we condition on X and S instead? Well, it closes two of the pathways by which age influences stroke, and all we're left with is this direct effect of age on Y, which may be tiny, yeah. It may be that it mainly operates through the other effects. So what I want you to see from this example is that if you just make a table with the coefficients of the three slopes and invite the reader to interpret them all as causal effects, you'll be misleading the reader. You may also be misleading yourself. These coefficients need the causal model, they need the DAG or some other causal model so that we can make sense of them. And that's the table 2 fallacy, the fallacy of interpreting all coefficients as total causal effects. In the homework for this week, I'm going to ask you to analyze this graph again in the presence of an unobserved confound that I'm drawing here. And you'll use the same steps in the backdoor criterion. And again, I'm going to ask you to say what each of the coefficients means. Okay, let me summarize the table 2 fallacy here. So not all coefficients are the same kind of thing, even though structurally in the regression model they may look structurally the same. They're different because the causal model is what gives them meaning, and the causal model is not necessarily completely represented in the regression that you use. So what are we supposed to do then when we report our results? One option is simply not to present control coefficients, only present the estimand and the appropriate marginalized causal effects of interest. Another option is to give an explicit interpretation of each coefficient, and you justify that interpretation using the causal graph. Whatever you decide to do, if you don't have a causal model, then you don't have any interpretation of the coefficients at all. Okay, this has been a long slog. It's a very long lecture. I apologize, but I hope you had 2 intermissions, and I hope you made full use of them. Before we part for now, I want to say a few things that are on my mind about this topic. The topic of confounding and getting finding causal estimates, that is, identifying causal estimates, is actually very large, and it's not possible for me in this course to really address all the important bits of it. So I just want to measure a few things in passing for now, so you see that the horizon is large. There are going to be lots of analyses where you just can't credibly adjust for all the confounding. And in observational studies, it's quite common. And the systems are complex, and you can't measure all the causes of a thing. It'd be crazy to try. But that's not a reason to give up. Lots of very powerful scientific advances have been made by studying natural systems without experimental control. You don't have to get it right in one study. We can do it iteratively. So even a biased estimate can often be better than no estimate, because it gives us an idea of sort of an upper bound, if it were, on causal effects, and it helps us think through the system more. You can also do sensitivity analysis. I'll have an example of this later in the course, in the second half of the course. In a sensitivity analysis, what I mean is you draw the implications of what you don't know. So you can make different assumptions about the thing you don't know. How big could it be? And what effect would that have on our inference? When this comes to confounds, you can imagine different sizes of the confound, and you can ask questions like, how big would the confound have to be? Now, of course, we don't know how big it is, but how big would it have to be to explain away the measured association between a treatment and an outcome? I'll show you later in the course how to do that. And then another option, of course, is that you use your causal model analysis skills to realize that you can't get rid of all the confounding, and so you redesign your experiment, or you find a natural experiment. And that's another option as well. But it's very different than giving up. Okay, thanks for your indulgence. This is the end of week 3 of the course, and starting next week, I'm going to talk about overfitting, which is a very important topic in the relationship between prediction and inference. And I'm also going to introduce you to Markov chain Monte Carlo, which will lay the groundwork for everything we'll do in the rest of the course. And I'll see you there.